welcome you all to this capstone presentation here. My name is Wayne Kimura. I'm one of the faculty members who works with students. This particular presentation, I don't know if Marty mentioned to you, is rather special because this is the first time we've ever had to have two in parallel. Usually we just have only like 4 talks or something like that. We just have one session. Well, hell, today we were going to have 9. We actually had 8 talks, and there's no way that they could be done in series. So we split up into 2. Interestingly, this particular session only has my teams. So it's kind of nice. They're all 4 my team. And what that is nice in more ways than one is that I know these students very well. I know they worked very hard and are anxious to give you, to tell you what they shared with them. You'll find it very interesting. One of the things that I wanted to also do is to, if you ever watch the television news, they always like to use teasers. Get you, stick around. Okay. So on this particular talk, here's my teaser. And my teaser is that what do airplanes and trucks have in common? Well, in this case, they both use simulators, and we're going to talk about that. So I'd like to introduce this first team here. The title of the talk is Virtual Reality Truck Simulator, Linux in a Box. And the team members are Steve Gardner, Shay Joseph, Brian Overlay, and Ryan Regan. And I think, Brian, you're there? Yeah.
Shay's going first.
Shay's first. Okay.
So our capstone did Virtual Truck Simulator, Dynamics in a Box. As Wayne just introduced us, I'm Shay. This is Ryan. We have Steve and Brian over here. Our sponsoring company is PACCAR, and our mentor is John Dahl, and our advisor was Dr. Wayne D. Kimura. So the agenda for our presentation today includes an introduction of the company PACCAR, the motivation as to why we chose to do a truck simulator for our project. We go through the hardware and then the software separately of our project, and then we're going to talk about the results, our remaining tasks, and a reflection of capstone as a whole. So for our team roles, we have Steve over here. He was in charge of the software. I was the project manager and I helped with the hardware. Brian was in charge of software and hardware, and Ryan was mainly on the hardware side of the project. So to introduce PACCAR as a company, Kenworth is a subsidiary of PACCAR, and they're a leading company of the manufacturing, design, and production of premium quality trucks. They also are the design and manufacturers of the most efficient diesel engine on the market today. And they're global leaders in part sales and aftermarket parts distribution. So our motivation as to why we chose to do a portable truck simulator comes from PACCAR's need to be able to show their customers their software before implementing it into the production line. It allows for immediate feedback based off of visual display. And then pictured right here is an actual system PACCAR owns in office. It's called Dynamics Development Boxes. It's used to test their software inside the office. The system is valued at more than $20,000, so they needed a more portable version to show to their customers and a less expensive version, which is why we came in. And then we're going to have Ryan explain this to you.
Okay guys, so this is a basic system diagram. I'm going to go into more detail about the specific components, but this will give you guys an idea of what's going on. So we're taking simulated truck data from a real truck. It's recorded on an SD card, and our project was to take that data and turn it into electrical signals that are sent to a main controller in the truck, and that controller will send the information to an instrument cluster, which will display the vehicle speed, the RPMs, and other important information. But before we get started, I wanted to give you guys a background on CAN, because CAN is something that's heavily used in the automotive industry. It's basically a data bus that allows microcontrollers, or not microcontrollers, but controllers to communicate with each other via a twisted pair of wire. We use SAE J1939, which is a set of standards that defines the physical CAN bus. So how to connect devices to a CAN bus, how long a CAN bus can be. Defines how a message is constructed. So a CAN message has a priority. It's called an identifier. It has a priority, a PGN, which is basically what the message is, a source address, and a destination address. And then, so for example, a message could be your engine RPM, and then the data for that message would tell what that engine RPM is. Some of the hardware components that we use, the main component, the main computer in the truck is called a CECU. It's a cab electronic control unit. We also have a chassis node, which is the main controller on the frame of the truck. And the instrument cluster, which is this guy down here, displays the vehicle speed, RPM, and other information. One unique thing about the Kenworth cluster is right here where you can't see, there's a display menu, which gives you a digital readout of your engine speed, RPMs. There's also features that help a driver determine the most fuel efficient time to shift the vehicle. And we have a menu control switch, which controls this thing. We use an Arduino and a CAN bus shield to take information from a log file that was stored in text and convert that information into real electrical signals to put onto a CAN bus. We use a 12-volt power supply, which is standard in the automotive industry in America. And we had our project includes a diagnostic connector. This is used for PACCAR they can monitor the CAN bus, and they can also flash different components with software updates through the diagnostic connector rather than taking them out of the box. And then we had a variety of switches and potentiometers that we use to simulate different inputs to the controllers on the truck, like park brake switch or your fuel level. So here's another system diagram. So we're simulating recorded data on an SD card, which is stored in the Arduino. So what the Arduino does is parses that file, converts it into real signals, and puts it onto this CAN bus. The CAN information is sent to the CECU. The CECU takes that information, forwards it to the instrument cluster, and the instrument cluster is repeating what an actual truck was doing and simulating what a truck was doing. Here's a little bit more detailed circuit diagram of what we did. I'm going to go over some of the hardwired inputs to the CECU. Steve's going to give a greater explanation of the software. But there are a number of switches that we have in our project and potentiometers that were hardwired directly to the CECU. And I'll give you one example, is a headlamp switch. So what that is, it's an active low signal to the CECU. So you connect ground to a pin, and what happens is the CECU sends a message to the instrument cluster, and the lights dim on the dash, as they would if you were going down the road. I'm going to pass it off to Steve and let him go through some of the software.
So the software is all on the Arduino that we wrote. And we've got a reset and clear pause button. And essentially we're injecting the data here into the beacon, where normally we have an engine and some other things up here that are all connected electronically to the CECU. We are simulating all of those components by playing back the CAN data from the recording. We need to communicate the pre-recorded file to the instrument cluster. So the CAN messages in our text file all have timestamps, and they also have identifiers and the message, the data itself. The file has them at 1 to 10 milliseconds apart, which gives us our requirements for keeping up in real time. We've been playing up to 5-minute long CAN files, and they've been in real time so far because we programmed it that way. We had a lot of options At first, we were considering between Arduinos and Raspberry Pis, which are more powerful and faster. When we settled on Arduino, we had to choose between the Uno, the Due, and the Mega, which the main differences are clock speed, data bus size. For example, the Uno that we went with is 8 bits, whereas the Due is 32 bits. The Uno that we went with is 16 megahertz, whereas the Due is 96 megahertz. The Mega is a lot like the Uno, but it has a lot more RAM. And so the Uno, which we went with, has only 1 kilobyte of RAM, is 8-bit processor and 16 megahertz. And after some efficiency tweaking, we were able to make it to the 1 millisecond requirement and had plenty of room to spare. Here's our basic software flowchart. We start with the boot sequence. When you turn on the box itself, it gets power and it looks for the SD card. And once it sees it, it opens the file and will wait for the play button. And when you hit play, then it starts reading the CAN data from the SD card. It'll convert them for the CAN shield and it transmits to the CAN shield, which will send it when the time comes. And then it just keeps going until either you press pause and then it just holds off for a second, or until you hit play again. Or you can hit pause, stop, and it will go all the way back to waiting for the play button. And when you hit play, it'll start at the beginning of the file. Or it waits until the end of the CAN file, at which point it will again go back to this part. So some of the things that it does in the initialized stage of loading drivers for the CAN controller and for the SD card, it opens the SD card and searches for the can.txt, which is one of those requirements that we ended up doing, so we didn't have to add a display on there. It will always find can.txt. We had considered also being able to switch between different files, but that would have required additional hardware space on our project itself. When it hits play, it reads the buffer data. This is another one of those things that we needed to do for efficiency. It turns out that a short read takes about as much time as a long read from the SD card. So doing one bigger read of 256 kilobytes made it a lot faster rather than reading several times per line. And then we convert line by line timestamp identifying data. And the timestamp we compare with the internal clock of the Arduino to wait until we need to send the message. I'm going to pass it off to Brian now, who's going to talk about some of our results.
So this is just a high-level overview of our design layout, and our box is over here. But if you imagine the box, this would be like the bottom of it underneath the instrument cluster. And so up here you can see the chassis node, the power supply, the CECU, and the Arduino, and all of those components are what are making the truck think that it's, or part of the components that are making the truck think that it's actually a truck. On the top, if you opened up our box, you would see the actual instrument cluster, which is the dotted gray area. And this was a pre-layout for what we wanted to do. In our final product, it was a little bit different, which I'll show next. But down in the bottom corner, you have that MCS switch that Brian had mentioned to cycle through the driver rewards and the LCD screen up top. And then we have some power switches, the play pause button, the diagnostic connector, and like our potentiometers and other switches to control some of the inputs and outputs on the system. So just a kind of an overview of the results. Our project is working, and we successfully integrated all of the hardware and software together, so we can read an SD card that has a CAN file on it and then play it, and it looks just like it's driving down the road. We also demonstrated that the timing of the simulation was accurate. There weren't any errors between CAN data messages being sent along the CAN bus. And our original budget that Packard had given us was around $1,000, and we were well underneath that. So I'll get into that in a second. I don't know if I can play this one here, but don't play it yet. So this is what our instrument cluster looks like, the top of our project. And this video in a second will go over just some of the functionality of it, but Like down here, you'll have a headlight switch, your park lamp switch, you have potentiometers for fuel, and then there's primary and secondary air down here. And so the primary and secondary air are over here, fuel is right here, and then there will be lights that'll light up on the instrument cluster if you pull the park brake switch or the headlamp switch. And then this switch over here is the dimmer switch, so like when you turn your headlights on, when you're driving at night or whatever, you can dim the brightness of this screen up here. Yeah, go ahead. So right now he's changing the headlight switch, and you can see that the brightness was being adjusted. And then he just changed the park brake switch, which you can see that lamp showing up right there. Right now he's going through the MCS, just showing the different menu features that it has on the screen up here. And then next he's going to adjust the fuel gauge, which you can see right here. You see it move slowly, slow input. And then next the primary air, which will be up here. And then the secondary air, you can see them kind of moving up there. So it's functional, it works, it's exactly what we were looking for. And then obviously our project was to simulate a truck driving down the road. So we also drew in a short clip of it actually driving down the road. And what you'll see it happen is it'll be idling, the engine RPMs will be idling right here as if the truck's just sitting in place, and then you'll see it start to accelerate, and the RPMs will start increasing, and then it'll shift, and it'll decrease, and then increase again, and you'll see the speedometer going back up. And all this is going to do is accelerate up to 45 miles an hour, and then go into cruise control. You can see up on the driver display that it's showing miles per hour digitally. And then also, I don't know if you can see these 3 green dots right here, and how the RPMs are staying within that range. It's the most fuel efficient RPMs for the truck to be driving down the road. And then it was also just switched over to RPM, so you can see that digitally as well. That's LCD that they have, and all of the features that you can do within it is really neat. So just to go over our results that I just mentioned, our real-time accuracy was, we basically compared our file for our simulator with one of Kenworth's larger simulators that Shay had mentioned earlier that were like $20,000. And over the course of 5 minutes, we were always within about a few seconds of the actual video. So you calculate that out, it's about 1% accuracy, which to any driver, you're not going to notice that difference. So we were definitely within the real-time accuracy. And then also in terms of just actually playing the log file, when we first started, we did have some errors, like Steve had mentioned about the buffer, how we figured out that we could take a larger amount of the buffer instead of just a little amount of the buffer. When we did a little bit of amount, we would actually have missing messages. And so when we changed and implemented the larger buffer, we were actually able to get everything to play through how it's supposed to be, and we weren't skipping any messages, which was nice. That's exactly what we wanted to do. And then our cost, again, I said we had about a $1,000 budget, but as you can see from all of these components over here, the Arduino Uno, the CAN shield, the SD card, the extension for the SD card, just simple components, we were well under $1,000, not even at 100. So PACCAR's probably pretty happy about that. And then also, portability was another big one. The machines that they have right now are not portable, or I mean, I guess they could be, but it would be a real big hassle. And our box, you can just lift it up and carry it around. So we met all of our design requirements. We did have some ideas for if another team ever wanted to go into this, some future development. Some minor changes were, right now, as you can see the handles on the side of the instrument cluster, you just lift up the entire bezel, and then that's what gives you access underneath. So we thought maybe you could throw some hinges along the back and just have it swing up, just, aesthetics really. Also, our SD card extension cord that we have, we didn't mount it on the top. So that's another minor fix that we could have done, is just cut a hole and actually mount the SD card slot, so you don't have to lift up the bezel to put a new SD card in or whatever you wanted to do. Some major things that could be implemented on this are dynamic switches to make it more interactive. Right now, this is solely just a playback. So, I mean, you technically could play something that would simulate dynamic, but it wouldn't actually be dynamic. So if another team wanted to add some more switches in, like for cruise control, for instance, turn on cruise control and then you can have it play out in cruise control, and then once you turn that off, then it will go back to whatever the log file was before. And then another big one would be video. That would probably be the biggest change to this project. So instead of just looking at the RPMs and the speedometer and watching it drive like that, you could actually see a video of maybe like from inside the cab of a truck driving down the road, but also doing exactly what our simulation is doing. So Capstone, as a whole, we got a lot out of it. I mean, we got to work in a larger group for 2 quarters straight, and that's not something that you typically get out of the EAP program. If you're just doing labs or something, those are typically a couple of weeks. So this was 6 months of grinding and getting things done. So that was great hands-on experience and a great learning experience, especially for going into the working world. Just doing a project from start to finish, again, comparing to labs. I mean, typically labs, you're pretty much given the path to the solution, if not completely, almost, So this was something that we almost went in blind with the help of John and PACCAR and everything. We definitely got some guidance, but to do a project from start to finish, got a lot of problem-solving skills out of that. Definitely time management, the collaboration again was another big one. And really, any advice for future Capstone teams would be the biggest success factor for us was that we set hard deadlines early on, and we didn't set them towards the end. We almost made them unrealistic. So instead of waiting until the very end to have a bunch of really late nights, in the beginning of the quarter, we would have a bunch of late nights to meet those deadlines. So that really helped us get this project done. So some of the things that we learned from this project, we learned a lot about CAN, which is a great serial communication between computers. We also learned more programming skills using the Arduino. A lot of people don't consider it to be a true programming language, but if you look behind the scenes, it's really C and C++ and all of the source files. So I personally think that argument is invalid. But, for our hardware skills, we learned all kinds of wiring connectors. Even on some of the computers, they have like the small connectors with the really small terminal pins, so crimping stuff like that. Ryan did a lot of the mechanical stuff, drilling the bezel. So we learned a lot from this project. It was great. We'd like to thank Kenworth and John Dahl for sponsoring our project. It was a great help throughout the entire process. Very knowledgeable, especially when we didn't know what was going on in some cases. David, Mitch, and Jennifer, all people that work at PACCAR as well. They helped us with learning more about CAN and getting things reprogrammed if we needed reprogramming. Like for instance, when we first got everything hooked up and we tried to turn it on, nothing worked, and we were like, what's going on? And then we thought, and then got suggested that the CPCU hadn't been reflashed. So we ended up going to PACCAR and getting it reflashed, and we got help for that, which was great. Steve Yons up at the PACCAR Technical Center, he was mainly the person that this project was for. he was the one that wanted to get the ball rolling on this, and he set the guidelines and the requirements for everything that we needed to do with this project. And we'd also like to thank Dr. Wayne Kimura. Been a great help this whole time, always guiding us, pushing us to do better. Yeah, thank you.
Okay, are there any questions? You all know how to drive a truck, right?
How much code do you have to write, and how was that process debugging the code or something like
It was only a few hundred lines of code. We actually were able to find open source software with free licenses for driving the CAN bus and the SD card, because we didn't need to reinvent the wheel for those. It's included in loading the drivers for those components. The code itself for reading and parsing and then sending wasn't very long. Any other questions? Thank you.
Well, wait a minute,
Oh.
Can't let you guys get off that.
Yeah.
Actually, this is a warning to the rest of my team, I'm gonna ask the same question. Which, as a mentor for this, I'm always like to learn the following. What did you find one of the most noteworthy things you learned from this capstone project that you would have not learned in your regular class?
Well, one of the things was learning about CAN, communication protocol. It's something that's heavily used in the automotive industry, and we knew nothing about it. So,
Okay. Any other in terms of general things, in terms of skills or whatever you learned?
It's okay. Now that I'm on the spot, I can't.
One of the things that we had access to that we used were real schematics from PACCAR and also their software lists of components and stuff, which in classes we have like this big, and they're just circuit diagrams in really nice big bold font with everything labeled. And PACCAR's, they're very detailed, very large piece of paper that were much harder for us to learn how to read at first.
Yeah, because they're multiple pages and they're referencing to other pages, so it's not just a simple schematic that we can see.
Basically, real life exposure to real life. By the way, I want to introduce John Dole, who was their instrument. Thank PACCAR. PACCAR has sponsored other capstone teams. We're very thankful for the sponsorship. This was a great opportunity for this team. Thank you very much.